Hello, and thank you for tuning in. This is our 32nd episode in our series of Vertex Operator Algebras. We are in the back half of Chapter 2, covering some background material for the physical manifestation of the so-called formal series, known as conformal fields. Today, we'll be looking to apply Noether's theorem, which we discussed last time, to the two-dimensional case of a conformally invariant field theory. To ease the transition from our discussion of Noether's theorem from last time, we'll begin in 4 dimensions, or 3 + 1 dimensional space, with time signaled out as a +1. Indeed, there are 2 distinct ways of looking at spacetime, which are isomorphic as vector spaces. There's the Minkowski, or physical spacetime, whose metric implies a sort of hyperbolic geometry. And of course, the Euclidean, or thermal spacetime, whose metric is the familiar one on R4. You can pass between these 2 manifestations by taking the time dimension to be explicitly imaginary. The line element of Minkowski space has the characteristic change in signature, which for today's lecture we've reversed all the signs. This change of choice happens all the time in physics and isn't ultimately meaningful. What is meaningful, of course, is the difference between Minkowski and Euclidean signatures, as presented here in the line element S sub e. The metric used to form these line elements and contract, raise, and lower indices in our vector calculus is diagonal, and has the same signature as the line segment. Fun fact, sometimes imaginary time has the interpretation of temperature, when, for example, we pass from quantum field theory to statistical mechanics. You might remember that the dynamical fields of interest are fibers over the spacetime base, and so the symmetries you might infer from the line segment are actually those of the spacetime base. For Minkowski space, those symmetries are the 3-dimensional rotations, represented by the group of orthogonal matrices, the translations, which are hopefully self-explanatory, and the so-called Lorentz boosts, which are essentially rotations between space and time coordinates. Now, we can include the spatial rotations in with these to form the Lorentz group of 4-dimensional rotations, which is again represented by orthogonal matrices. We can extend this so-called affine symmetry to include other transformations if we agree on less strict requirements. For example, if instead of transformations that preserve the line element, we allow transformations that preserve the line element up to an overall scaling factor, we get the so-called conformal group of transformations. The infinitesimal version of those transformations can be represented by an infinitesimal diffeomorphism of the base, epsilon, subject to the new line element condition. This, in turn, provides an equation for epsilon, an equation worth referencing later, so we'll name it here with a lightning bolt. Also, here d is the total number of dimensions of our base space. As an exercise, you may show that this lightning bolt equation implies a 3rd-order differential equation for epsilon, from which we derive 2 observations. First, a generic solution, epsilon, is at most of order x squared. Second, something special happens when the number of spacetime dimensions is 2. In 2 dimensions, we find that the lightning bolt equation simplifies. Note the presence of the metric, which requires a choice of either Minkowski or Euclidean signature. Fortunately, most everything we study won't depend too much on this choice, as we can always arrive at the other by scaling time with I. But it is certainly easier to work with an explicitly Euclidean metric, as the lightning bolt equation essentially reduces to the Cauchy-Riemann equations familiar from complex analysis. You might want to prove that last statement as an exercise. Going forward, we'll work with the holomorphic coordinates z and z bar. Now, here's a bit of warning about these coordinates in the physics literature. Factors of 2, or square roots of 2, or inverses of square roots of 2 are rampant in different authors' conventions. We'll stick with the Ginspard convention here, as it also appears in the famous Green-Shorts-Witten book on string theory. Note that in this convention, the inverse metric is not necessarily the same as the metric itself. Also, the I in these linear combinations is not the same as the I used in transforming Minkowski to Euclidean space. Also, for you fans of niche historical physics, these holomorphic coordinates are the analog of the so-called light cone coordinates from Minkowski spacetime. Now, conformal symmetry, locally, amounts to a holomorphic transformation of the coordinates. For a map, z goes to f of z, and its anti-holomorphic counterpart, the two-dimensional Euclidean line segment is scaled by the modulus square of the derivatives of f. As with Ginzburg, we've been careful to call this a local symmetry because we worry a little bit about poles, particularly when considering fields. Now, a basis of symmetry generators for these transformations is given by the differential operators L sub n and L sub n bar, where sometimes we use the Debot operators as a shorthand for d by dz and d by dz bar. These operators form a hopefully familiar algebra. Indeed, we find the local conformal symmetry algebra amounts to 2 copies of the Witt algebra. Note that in the quantum theory, these algebras obtain a central charge and extend to 2 copies of the Virasoro algebra. In case you might have wondered why we were talking about any of this. In his notes, Ginzburg makes the remark worth pointing out here. Let A be either the Witt or the Virasoro algebra, depending upon context. The direct sum of A and A bar acts on R2, but can also naturally be extended to an action on C2. And so we often purposely confuse the variable z bar with an independent complex variable, so our studies henceforth will often naturally sit in C2. But of course, we can always pass back to the quote real world, unquote, by enforcing a reality condition to project us back down to R2. This is akin to solving a physical wave equation with a complex valued function e to the ikx, and then projecting back down at the end of the calculation to, say, cosine kx. I've got my own remarks on this remark to make. First, this assumption can lead to quite a bit of trouble when you consider, unusual applications of two-dimensional conformal field theory. Like, for example, to the study of 2 + 1 dimensional quantum gravity. Not to give too much away right now, but I can't resist pointing out the famous result of Brown and Hanot, where the classical theory of gravity in 2 + 1 dimensions has 2 copies of the Virasoro algebra with central charges proportional to the ratio of the gravitational constant and the anti-de Sitter radius. This is an asymptotic symmetry algebra around a sort of hyperbolic version of Minkowski spacetime in 2 + 1 dimensions, and we will have much to say about that in the coming weeks to months. Probably months. Now, let's consider the application of Noether's theorem to two-dimensional fields. Consider some field phi, a function of the holomorphic coordinate z, over two-dimensional spacetime. We can derive the stress-energy tensor from translations, following exactly the same logic as we did last time. Last time, we studied the scaling current, which is conserved if and only if the trace of the stress-energy tensor vanishes. Now, scaling transformations are a subset of conformal transformations, those things which preserve the line element up to an overall scaling factor. These also include something that can be thought of as inversions, I guess, which have a similar Noether current. To make contact with our studies today, we aim to pass a stress-energy tensor with Euclidean coordinates with holomorphic indices, which you are encouraged to verify as an exercise. Indeed, using the tracelessness required by conformal invariance and the transverse property of T we discussed last time, coming from translation invariance, you can show that dz on T z bar vanishes, much like dz bar on T z. Put differently, perhaps more clearly, T breaks into 2 separate terms, a holomorphic and anti-holomorphic term. And as it turns out, T and T bar generate the full set of local conformal transformations in 2 dimensions. Just as vectors and spinors form representations of the orthogonal group of rotational symmetry in R3, we shall find irreducible representations of the conformal algebra in terms of fields phi of z. Well, and their derivatives, of course. But those details will have to wait for another time. We'll close today by distinguishing between local and global conformal symmetries in Euclidean 2-dimensional space. We'll do this by matching operators with known global symmetries. Translations, of course, are constant shifts, and so are generated by the L-1 terms. Remembering, of course, that L sub n is proportional to z to the n+1. Rotations, as it turns out, are combinations of L0 generators. And scalings, or dilatations, or dilations, depending upon what country you live in, are the other combination of L0s. Note that the irreducible representations of the conformal group will essentially be fixed by the eigenvalues of those L0 combinations. The so-called special conformal transformations, or conformal boosts, or if you like, inversion-ish transformations, are generated by the L1 operators. They're a little complicated to write down, but, integrated, they look something like this, where here the vector b parameterizes the transformation. Now, why focus on these special transformations? Well, any vector field generated by L operators with n less than -1 is manifestly singular, so they cannot represent global symmetries. And because of the special conformal transformations, we can also consider the map z goes to -1 over z, which means that v of z is singular also for any n greater than 1. Thus, we find that globally defined vector fields generated by symmetry transformations are precisely those previously discussed. The same, of course, goes for the anti-holomorphic case. These vector fields are non-singular globally on the Riemann sphere, that is, C with a point at infinity included. These global transformations can be packaged into an SL2C matrix, which represents the holomorphic map parameterized by 4 complex numbers, subject to the constraint that the determinant of the matrix is non-vanishing. From this perspective, you might begin to see where the relationship between conformal field theory and kind of modular stuff, our raison d'etre for studying vertex operator algebras, sneaks in. As we can, of course, simply consider the subgroup SL2Z, which affords us the modular transformations on the upper half plane. Indeed, we'll see other Riemann surfaces present in our study of conformal field theory, notably including the torus. But, of course, all things in due course. And that's our show. Next time, we'll start to crack open conformal field theory by looking at an algebraic construction of quantum mechanics.